All right, in my last video I introduced the idea of the derivative. We determined what the derivative of the function x squared was using the formal definition, otherwise called the limit definition of the derivative, and the work for that is shown right here, just to catch up. In this video, I'm going to introduce 3 limit rules and prove all of them, show where they come from. That is going to allow us to take the derivative of any polynomial function. So let's get started. Right, the first thing that's going to help us in this endeavor is going to be the sum rule. So if we have a function f of x that is defined as the sum of 2 other functions, in this case g of x and k of x, can we find some way to differentiate that? So in order to start with this, we know that the formal definition of a derivative is f prime of x is going to equal the limit, as h approaches 0, of f of x plus h minus f of x over h. So what would f of x plus h be in this case? Well, if f of x is g of x plus k of x, that would just be g of x plus h plus k of x plus h. And then what would f of x be? Well, it's given right here, it's just g of x plus k of x. And this will be in parentheses. All of this will be over h. Once again, this is just f of x plus h right here, and this is f of x. So we can move things around in here and sort of organize things by function. I can put g of x plus h by g of x. Let's go ahead and do that now. So this would become the limit as h approaches 0 of g of x plus h minus g of x plus k of x plus h minus k of x. Remember, you would have to distribute this negative. All this would be over h. And we know, based off of our limit properties, that the limit as h approaches 0 of the sum of 2 functions is equal to the limit of each of those functions added together. I have a whole hour-long video on limit properties, so if you're curious how we prove that, you can take a look at that video. But basically, this is equal to the limit as h approaches 0 of g of x plus h minus g of x over h plus the limit as h approaches 0 of k of x plus h minus k of x, all of that over h. And what is this? What does this look like? Well, this is just the formal definition of the derivative, but for g of x. And this is just the formal definition of the derivative for k of x. And so what does this equal? Well, this tells us that f prime of x, the derivative of f of x, is just going to equal the derivative of g of x, or g prime of x, plus the derivative of k of x, or k prime of x. And this is excellent news, because this means that if we have some function and we can break it down into a sum of 2 other functions, so for instance, let's say that f of x was equal to 5x plus x cubed, now we know that this f prime of x is just going to equal the derivative of 5 of x, or 5x, plus the derivative of x cubed. So that's great news. This is going to make our work a lot easier. Let's press forward a little bit here. The other property that's going to be useful for us is going to be the constant multiple law. So if f of x is equal to c times g of x, and c is just some constant, can we find f prime of x, or the derivative of f of x with respect to x? And so let's see if we can work this out. Well, in this case, f prime of x, just like before, is going to equal f of x plus h minus f of x over h, the limit of all of that as h approaches 0. And in this case, what's f of x plus h? Well, it's just c times g of x plus h. And what's f of x? It's c times g of x, all of this over h. And the key thing here to realize is that this is just the same thing. So the limit as h approaches 0, so constant multiple times g of x plus h minus g of x, all of that over h. And once again, because of our limit properties, which was proven in my video on limits and limit properties, we know that the limit as x approaches a, c times f of x, assuming that c is some constant value, this is going to be equal to c times the limit as x approaches a of f of x. And because we know this, we could pull this c out of the equation, and this tells us that it's equal to c times the limit h approaches 0 of g of x plus h minus g of x over h. And once again, this is just our definition for the derivative of g of x. So in this case, f prime of x is just going to equal c times g prime of x. Where does this come from? G prime of x is just this expression right here. That's the formal definition for g prime of x. And then there's that constant multiple out front. So in practice, this would tell us, just for example, because we know the derivative of x squared, if we had that f of x was equal to 5x squared, then f prime of x would equal 5 times the derivative of x squared with respect to x which we know is just 2x, so this is going to equal 10x. Probably our most laborious undertaking is going to be proving the power rule. We were able to show what the derivative of x squared was, and we might even be able to show what the derivative of x cubed is pretty easily, pretty succinctly. But as these powers of n grow to higher and higher numbers, this is going to become harder and harder and harder to prove using our formal definition of the derivative. So we want to see if we can find a way to prove just the derivative of x to some arbitrary power, in this case we're using the variable n, for any value of n, to make our life a little bit easier. So let's do it. All right, so just taking a crack at this with our formal definition, we'll have that f prime of x is equal to the limit as h approaches 0 of f of x plus h. Well, what's that in this case? That's going to be x plus h to the power of n minus f of x, which is just x to the power of n, divided by h. Another complicating factor here is this x plus h to the power of n, because x plus h to the power of 1, x plus h to the power of 1, that's just going to be x plus h, obviously. And then you have x plus h squared. That's going to be x squared plus 2xh plus h squared. Then you have x plus h to the power of 3. I encourage you to work this out on your own. You could just take this and multiply by x plus h. But you're going to get x cubed plus 3x squared h plus 3x h squared plus h cubed. And you could do this further. You could get x plus h to the power of 4. And that would be x to the power of 4 plus 4x cubed h plus 6x squared h squared plus 4x h cubed plus h to the 4th. And you can keep going in this fashion. We clearly cannot do this for some arbitrary value of n, because that will extend on forever. And so we need to think of some way to generalize this expression. Right? And so what patterns can we notice here? Well, we notice that as we increase the power of n, it appears to me at least, you could think hypothetically that there would be some h to the power of 0 here and an x to the power of 0 here, because that's just equal to 1. You could include that here as well. And you could go down the line and add this into every one of these. Some h to the power of 0, some x to the power of 0. And when you add that in, it becomes a little bit more obvious that with each term in here, you begin with x to the power of n, right? And it's being multiplied by h to the power of 0. Then the next term, you're getting x to the power of n minus 1. So in this case, our second term is going to have x, for our x plus h to the power of 2, our first term will have x squared, x to the power of n. Then our next term will have x to the power of n minus 1, and h to the power of 1. And then with each one of these expressions, you will just continue on in that fashion. So it will begin with x to the power of n and go all the way down to x to the power of 0, and it will begin with h to the power of 0 and go all the way up to h to the power of n. That seems to be the pattern. And so x plus h to the power of n, we can generalize. We can say that this is going to equal x to the power of n plus, and then it seems like the coefficient in the second term is always the power that we're raising it to. X plus h to the power of 2, we have 2 is the coefficient in our second term. Power of 3, we have 3 as a coefficient. So we can write that our coefficient would be n times x to the power of n minus 1 multiplied by h to the power of 1, which is just h. And then there's going to be a bunch of other terms here all the way down to h to the power of n. This is our generalized expression for x to the power of n. X plus h to the power of n. And you might be stumped here in realizing that, well, what do we think of these coefficients? How do we arrive at these coefficients? And you might be tempted to bust out the binomial theorem, saying that x plus h to the power of n is equal to the sum from k is equal to 0 all the way up to n of n choose k, this formula that derives from the counting principle for these two variables multiplied by x to the power of n minus k times h to the power of k. And while this is true that this will yield each one of these formulas, it's actually not necessary to bust out the binomial formula, the binomial theorem. It's not necessary because what we can realize from this expression right here, let's just plug this in for x plus h to the power of n and see what happens. Well, what we're going to get is we'll get that f prime of x is equal to x plus h to the power of n, which here we're saying is equal to this here. I'll just leave it in green. It's going to be x to the power of n plus n, oh sorry, I left out a very important part before we move forward. F prime of x is going to equal the limit as h approaches 0. Don't want to forget that. Now we can add in our x plus h to the power of n. We get x to the power of n plus n, x to the n minus 1 times h, plus some other stuff all the way down to h to the power of n. And then from the rest of our definition, we're going to subtract f of x, which in this case is just x to the power of n. We're going to divide the whole thing by h. We're going to divide the whole thing by h. And now what happens? Well, x to the power of n here is going to cancel. Maybe we can do this in a different color. It's going to cancel with this x to the power of n. And this is what we're left with. We're left with a series, f prime of x is equal to the limit as h approaches 0 of n x to the n minus 1 times h plus a bunch of other terms that interestingly all have h to the power of something higher than 1. The first term is going to have h to the power of 2, then h to the power of 3, then h to the power of 4, all the way down to h to the power of n. That's going to be the rest of the terms here. And then this whole expression is going to be divided by h. And what we can do is we can actually factor out an h of this top equation. This is going to equal the limit as h approaches 0 of n times x to the power of n minus 1. Sorry, I'm forgetting something again. We pull out the h, and we say that this is n times x to the n minus 1, plus a bunch of other terms that are going to have h in them, all the way down to h to the power of n minus 1, because we factored out this h. And then we can actually cancel out these h's. Those are going to cancel. And now what are we left with? We're left with the fact that the f prime of x, the derivative of f of x, is going to equal the limit as h approaches 0 of n x to the n minus 1 plus a bunch of other terms that all have h as a factor. The first one's going to have h as a factor, the next one's going to have h squared, all the way down to h to the power of n minus 1. And what's going to happen, now we can just plug in h for direct substitution. All of these other terms are going to go to 0 as we take the limit as h approaches 0, and we're going to be left with the fact that f prime of x is equal to n x to the n minus 1, and that is our power rule. So now that we've proven this expression, the derivative of x to the power of n for any value of n is just going to be equal to n times x to the power of n minus 1. And we've proven that the derivative of the sum of two functions is just equal to the sum of the derivative of those two functions. And finally, we've proven that the derivative of a constant multiple by some function is just equal to that constant multiple by the derivative of that function. Now that we know all three of those, it becomes pretty simple to solve problems like this, and you don't even need to consider the formal definition of the derivative. We could tell just by looking at this that the derivative is going to equal, well, it's going to be 3 times the derivative of x to the fourth, which is just 4 times x to the power of 4 minus 1, which is 3. So this is going to equal 12 times x to the third, minus, all right, let's see here, 5 times 2 is 10, times x to the power of 2 minus 1, well, that's just 1, so we'll just leave it as x. And then we have, well, x to the power of 1, x to the power of n minus 1 would just be x to the power of 0, which, well, that's just equal to 1, so the derivative of this is just going to be 8 times 1, which is 8. And what's the derivative of a constant? This is something we didn't cover, but this is pretty simple. If g of x is equal to some constant, g prime of x will equal g of x plus h. What's that? Well, that's just going to equal, let's see, limit h approaches 0. G of x plus h in this case is still going to be c, and then g of x is going to be c as well over h. Well, this is just equal to 0. So the derivative of a constant is 0, and that should make sense. This derivative is measuring the rates of change of a function at given points in time, and the rate of change of a function which doesn't change is going to be 0. And so with these laws in mind, we've taken something that tends to be a pretty arduous process. The formal definition of the derivative can be pretty complicated. For example, showing that if h of x was equal to x cubed, finding h prime of x in this manner, the limit as x approaches, or sorry, not x, the limit as h approaches 0 of x plus h cubed minus x cubed over h. Working all of this out algebraically and proving this, although not impossible, is pretty time consuming, and it's even more time consuming for powers that go beyond 4 or beyond 3. That's pretty time consuming. But now that we have this arbitrary rule, we can do that very quickly, and we can do problems like this in a matter of seconds. So we take the derivative of any polynomial. The other thing that we could do is if we have the square root of x, we know that that's just equal to x to the power of 1/2, and you can show with the power rule that the derivative of this, the derivative of the square root of x with respect to x, or the derivative of x to the power of 1/2, because these are two equivalent expressions, this is going to equal to 1 over 2 times the square root of x. You can show that. And you can do the same thing with any roots. The cubed root of x, that's just equal to x to the power of 1/3. And you can show the derivative of this using our derived power rule as well, because this is a n that you can use. So it's just going to be 1/3 times x to the power of 1/3 minus 1, which is negative 2/3. So in conclusion, with just these three rules, you should now be able to take the derivative of any polynomial expression, any root expression, any power that x can be raised to. You could take the derivative of all of those equations. And in addition to that, you can take the derivative much, much, much quicker. Now you don't need to consult the formal definition every time. You can look towards these rules that we have derived ourselves and proven ourselves. Stay tuned. In future videos, we're going to discuss the derivatives of trigonometric functions, exponential functions, logarithmic functions. We're going to talk about implicit differentiation. We're going to talk about the chain rule, the product rule, tons of other fun stuff.